Step outside tomorrow morning, find the furthest line where the Earth intersects the sky. Do not search for a bird, a cloud, a vehicle. Lock your visual field on that static boundary for 2 minutes, 120 seconds. You will feel a change before you can name it. A drop in muscular tension behind your eyes, a shift in your breathing, a quieting of the internal noise that you did not notice was there until it stopped. You are not experiencing mindfulness. You are not relaxing. You are executing a hardware reset. The visual system of the human primate is not a camera. It is an exposed component of the central nervous system, built to receive specific frequencies and spatial geometries to calibrate the internal oscillator of the body. When you compress your visual field into a two-dimensional rectangle, sitting 40 centimeters from your face, for 16 hours a day, you are running an engine at sustained load without its maintenance cycle. The horizon is the mechanical override. The first mechanism begins with the structural engineering of the eye and the physics of light. Vision is refraction. Photons bounce off an object, enter the cornea, pass through the aqueous humor, and strike the crystalline lens. If the object is close, a phone, a book, a screen, the light rays are diverging. They are spreading apart as they travel. To focus those diverging rays onto the retina at the back of the eyeball, the lens must change its shape. It must become more convex. It must bulge. This process is called accommodation, and it is a mechanical action driven by the ciliary body. The ciliary body is a ring of smooth muscle tissue inside the eye, connected to the lens via a network of radial tethers called zonular fibers. When you stare at a screen 30 centimeters from your face, the ciliary muscle contracts. It acts like a sphincter, tightening its diameter. This contraction releases tension on the zonular fibers, allowing the elastic lens to thicken and increase its refractive power. Your eye is applying mechanical force to bend light. This is physical labor. It requires adenosine triphosphate. It generates metabolic waste. The ciliary muscle remains in sustained contraction for as long as you maintain that near focal distance. It is holding a weight. If you held a 5-kilogram weight at arm's length for 8 hours, the muscle tissue would fail. The ciliary muscle is subjected to this identical isometric load every day. There is a geometric threshold where this load drops to zero. In optics, it is called optical infinity. For the human eye, optical infinity begins at approximately 6 meters, 20 feet. When you look at an object farther than 6 meters away, the light rays arriving at your cornea are no longer diverging, they are parallel. Because the rays are parallel, the baseline refractive power of the cornea is sufficient to focus the light directly onto the fovea. The lens does not need to intervene. When you look at the horizon, the ciliary muscle completely relaxes. The sphincter widens. The zonular fibers pull taut. The crystalline lens is pulled flat into its resting state. The engine idles. It is the cessation of muscular torque within the optical cavity. This mechanical release is not a byproduct of looking at a distance. It is the primary maintenance cycle for the structural integrity of the eyeball. Chronic near work forces the eye to adapt to sustained tension. The biological response is axial elongation. The eyeball physically lengthens to permanently alter the focal plane. That structural deformation is classified as myopia. Looking at the horizon arrests this deformation. It breaks the circuit of continuous tension. But there is a second mechanism operating through the same optical hardware at the same time. This second mechanism has nothing to do with rendering an image. It is a photon counting system, and it regulates the timing of every organ in your body. For decades, the biological model of the human retina was considered complete. 2 types of photoreceptors, rods for low-light vision and motion detection, cones for high-resolution color rendering. The eye was a camera, but the camera model failed to explain a structural anomaly. There were blind individuals who had suffered complete destruction of their rod and cone networks. They possessed zero conscious vision, no movement, no color, no shape. Yet their bodies still perfectly synchronized their internal circadian rhythms to the external day and night cycle. The signal was getting in. The mystery was resolved through systematic electrical mapping. David Burson at Brown University, in 2002, published a paper in the journal Science, demonstrating that the retina contains a third, entirely distinct class of photoreceptor. They are called intrinsically photosensitive retinal ganglion cells, IPRGCs. They represent approximately 1 to 2% of the total ganglion cells in the human retina. In absolute terms, the human retina contains roughly 1.2 to 1.5 million ganglion cells. Of these, approximately 15 to 30,000 are IPRGCs. They do not form images, they do not connect to the visual cortex, they do not see. They measure the density of photons hitting a pigment molecule called melanopsin. Melanopsin is structurally optimized to absorb photons at a very specific wavelength, 480 nanometers. This is the exact frequency of blue light. It is also the exact frequency generated by Rayleigh scattering, the atmospheric physics phenomenon, where short wavelength sunlight collides with nitrogen and oxygen molecules in the atmosphere, scattering across the entire sky. The IPRGCs are physically distributed across the lower half of the human retina because the optics of the eye invert incoming light. Sensors on the lower half of the retina point directly upward. They are biologically engineered to point at the sky. When you step outside in the morning and look toward the horizon, you expose these upward-pointing sensors to a massive influx of 480 nanometer photons. The geometry of the morning horizon is critical. At dawn, the sun is positioned at a low solar elevation angle. Light must travel through the maximum density of the atmosphere. This atmospheric filtration creates a specific contrast ratio between the scattered blue light of the sky and the warmer, longer wavelengths coming from the sun itself. When a 480 nanometer photon strikes the melanopsin molecule, a physical transformation occurs. The photon delivers energy, causing the melanopsin to undergo a conformational shift. It twists. This mechanical change triggers a G-protein coupled receptor cascade. An enzyme activates, opening transient receptor potential channels, specifically TRPC channels, in the cell membrane. Sodium and calcium ions flow into the cell, altering its membrane potential. A voltage spike is generated. This electrical pulse does not travel to the visual cortex. It travels down a dedicated line called the retinohypothalamic tract. It bypasses the lateral geniculate nucleus entirely. It terminates in the hypothalamus, plugging directly into a cluster of approximately 20,000 neurons known as the suprachiasmatic nucleus, or SCN. The SCN is the master biological clock of the human organism. Inside these 20,000 neurons, specific proteins, clock, BMAL1, corticochrome, are synthesized and degraded in a negative feedback loop that takes roughly 24 hours and 11 minutes to complete. This is the endogenous period of the human circadian oscillator. Left to its own devices, without external timing signals, your internal clock drifts by 11 minutes every day. The electrical pulse from the IPRGCs is the reset button. When the signal from morning horizon light reaches the SCN, it forces the degradation of period and CCRI-pitochrome proteins, snapping the internal oscillator back to zero. The clock is calibrated. The SCN immediately acts on this calibration. It sends a descending signal through the paraventricular nucleus, down the spinal cord to the superior cervical ganglion, and back up to the pineal gland. The instruction is a strong graded signal: suppress melatonin synthesis. Melatonin is not a sleep hormone. It is a chemical marker of darkness. The pineal gland synthesizes melatonin from serotonin via two enzymes, arylecylamine, N-acetyltransferase, and hydroxyindolomethyltransferase, IOMT. When the morning light signal arrives, ANAT activity drops by more than 90% within minutes. Melatonin concentration in the bloodstream falls. The master clock informs the entire biological system that the dark cycle has ended. Simultaneously, the SCN signals the adrenal glands, located on top of the kidneys, to execute the cortisol awakening response. A sharp, high-amplitude spike in cortisol is released. In a study by Leproult and colleagues at the University of Chicago, an early morning transition from dim to bright light suppressed melatonin and produced an immediate cortisol elevation greater than 50% under controlled conditions. Figueroa and colleagues found that 1 hour of 800 lux white light in the morning increased cortisol levels by 35% compared to dim light. This is not the chronic, low-grade cortisol associated with psychological stress. This is an acute, necessary hydraulic pulse. Cortisol mobilizes stored glucose from the liver, raises core body temperature, and increases vascular tone. The system is pressurized and brought online. If you do not view the horizon in the morning, if you wake, look at a phone screen, and exist purely under indoor light-emitting diodes, the mechanism fails. Indoor lighting typically emits between 200 and 500 lux. A clear morning sky at the horizon, even before the sun crests, emits between 10,000 and 100,000 lux. The melanopsin circuit has a high activation threshold. This is an intentional design feature to prevent moonlight, approximately 1 lux, or brief lightning flashes from resetting the master clock. A phone screen, even at maximum brightness, delivers less than 100 lux to the retina because of the small aperture area. The photon density is insufficient to trigger the threshold. The TRPC channels do not open. The retinohypothalamic tract remains silent. The SCN drifts. Melatonin suppression is delayed. The cortisol awakening response is blunted. The organism operates in a state of biological ambiguity, chemically unsynchronized from the rotational physics of the planet, and there is a third mechanism operating on top of the optical relaxation and the circadian timing circuit. This third mechanism is dictated entirely by spatial geometry. It controls the autonomic nervous system. The human visual field is divided into two distinct processing streams, foveal vision and peripheral vision. The fovea centralis is a tiny pit in the macula, roughly 1.5 millimeters in diameter, packed densely with cone photoreceptors, approximately 200,000 cones per square millimeter. Foveal vision represents roughly 2 degrees of visual angle. When you look at a monitor, read a text, or track a moving object, you are utilizing foveal vision. This visual data is processed by the parvocellular pathway. Parvocellular neurons are small, have slow conduction velocities, approximately 2 to 5 meters per second, and are optimized for high acuity, fine detail target acquisition. From an evolutionary perspective, narrowing the visual field to a single localized point implies one of two biological states. You are tracking prey, or you are analyzing a direct threat. Consequently, the parvocellular pathway is neurologically tethered to the sympathetic branch of the autonomic nervous system. When you maintain a narrow foveal focal point, the brain interprets this visual geometry as a state of high demand. It activates the locus coeruleus, a nucleus in the pons of the brainstem containing approximately 50,000 noradrenergic neurons. The locus coeruleus pumps norepinephrine into the cortex, the amygdala, the hippocampus, and the hypothalamus. Heart rate variability decreases. Pupil diameter fluctuates. The system prepares for kinetic action. Looking at a screen forces the neurological system into a state of chronic sympathetic arousal. When you look at the horizon, you widen the visual aperture. You engage panoramic vision. By expanding your gaze to the lateral limits of the environment, without locking onto a specific target, you shift the processing load from the fovea to the peripheral retina. Peripheral visual data is routed through the magnoceal pathway. Magnoceal neurons are physically larger, 10 to 20 micrometers in diameter, compared to 5 to 10 for parvocellular, and possess thicker myelin sheaths. They conduct electrical impulses at 12 to 20 meters per second, 4 to 10 times faster than parvocellular neurons. They are not designed for fine detail or color. They are optimized for detecting low spatial frequencies, global motion, and broad field changes. The magnoceal pathway projects directly to the amygdala, the superior colliculus, and the pulvinar nucleus of the thalamus. Activating this broad panoramic visual field physically suppresses the locus coeruleus. It acts as an inhibitory brake on the release of norepinephrine. Functional magnetic resonance imaging studies have shown that wide-field visual stimulation reduces activity in the locus coeruleus and the sympathetic network. The parasympathetic nervous system, the circuit governing rest, digestion, and recovery, takes over. The vagus nerve releases acetylcholine onto the sinoatrial node of the heart, slowing the pacemaker cells. Heart rate drops. Blood pressure stabilizes. It is a rapid, predictable, hydraulic and electrical shift, initiated entirely by altering the geometric angle of light entering the pupil. It is a lever you can pull. The parvocellular circuit creates stress. The magnoceal circuit dismantles it. When you lock your eyes on the boundary between the earth and the sky, you are simultaneously engaging all three of these independent physiological systems. You are physically relaxing the ciliary sphincter, stopping the structural deformation of the eyeball. You are bombarding the IPRGCs with a massive density of 480 nanometer photons, firing a voltage pulse down the retinohypothalamic tract to reset the biological clock and synchronize endocrine output. You are expanding the visual field, activating the magnoceal pathway to suppress norepinephrine release and shift the autonomic nervous system into a parasympathetic state. Three separate biological imperatives, executed by a single mechanical action. Now the evidence calibration, because the three mechanisms described here sit at different levels of certainty. The melanopsin-driven circuit from the retina to the suprachiasmatic nucleus is highly documented. Berson's 2002 science paper identified the cells. Hattar and colleagues, also in 2002, showed that IPRGCs project directly to the SCN in both mice and primates. Gooley and colleagues in 2003 mapped the retinohypothalamic tract in humans using post-mortem tracing and demonstrated the connection. The effect of bright morning light on melatonin suppression and cortisol timing has been replicated in dozens of studies across multiple laboratories. This is not controversial. The structural degradation of the eye due to ciliary tension and the protective role of optical infinity is epidemiologically robust. The Yuan and John meta-analysis of 13 studies published in 2019 showed a 2.5-fold reduction in myopia incidence for each additional hour spent outdoors daily in children. Public health protocols in Taiwan, Singapore, and China now mandate outdoor time during school hours based on this evidence. The mechanism, axial elongation due to chronic near-work accommodation, is supported by biometric measurements of ocular length using A-scan ultrasound and partial coherence interferometry. The magno-cell suppression of the sympathetic nervous system via panoramic viewing is supported by functional imaging data, but the specific decoupling of foveal versus peripheral processing in natural outdoor viewing has not been isolated from the simultaneous effect of light intensity. A 2015 study by Labonte and colleagues measured pupil diameter, heart rate, and skin conductance during narrow versus wide visual field tasks, and found a measurable reduction in sympathetic markers during panoramic viewing. However, the precise neurotransmitter ratios and the degree of locus coeruleus suppression vary among individuals. The connection is anatomically plausible and physiologically coherent, but the direct evidence for the horizon as a specific intervention is weaker than for the first two mechanisms. The physics supports the connection. The independent variable isolation does not yet exist at the same level of rigor. This is how science refines itself, not by overstating what is known, but by specifying what has been measured and what remains plausible. There is a historical anchor worth including here. In 1938, Nathaniel Kleitman and his student Bruce Richardson entered Mammoth Cave in Kentucky to study human circadian rhythms away from external light. They spent 32 days underground with no access to natural daylight. Richardson volunteered to live on a 28-hour schedule to test whether the human body could be artificially entrained to a non-hour day. The results showed that even without sunlight, the body maintained a rhythm close to 24 hours, but it drifted, exactly as the SCN's endogenous period of 24 hours and 11 minutes would predict. That experiment, crude by modern standards, established that the human clock requires an external timing pulse. The horizon is that pulse. The difference between a healthy and trained rhythm and the drift observed in Mammoth Cave is the difference between stepping outside each morning and staying indoors under electric light. Think about what this means for the first 5 minutes of your day. The eyelids open, the cornea bends light, the iris meters aperture, the lens changes curvature, the retina converts photons into voltage. Melanopsin cells integrate brightness over time. The SCN receives a phase signal. The pineal night signal is suppressed. Cortisol rhythm is pushed toward daytime readiness. The vestibular system compares gravity with visual level. The extraocular muscles reduce convergence. The ciliary muscle reduces near-focus tension. The peripheral field comes online. The body is not being inspired, it is being synchronized. The horizon does not give you information in the ordinary sense. It gives your nervous system scale. Screens remove scale. A phone can show a mountain, a galaxy, a face, a war, a bank account, and a message from a person you love, all at the same optical distance, 30 centimeters. The emotional scale changes. The optical scale does not. The visual system is asked to process the universe through a near-field slot. The horizon restores physical scale. Distant objects produce small angular changes. Clouds move slowly. Buildings hold still. The visual field contains depth gradients. The eyes regain a relationship between object size, distance, motion, and body position. The system remembers that the world is not a feed, it is a space. The closing logic is simple. If the first light your eyes receive each morning is a ceiling bulb, the body receives a weak indoor approximation of day. If the first far object your eyes see is still inside a room, the visual system stays boxed. If the first task is a screen, the nervous system enters narrow symbolic work before it receives broad environmental calibration. None of this is moral failure, it is poor sequencing. Sequence matters in machines. Start a diesel engine cold under load, and the wear pattern changes. Feed a clock weak timing pulses, and phase noise increases. The body is not less mechanical because it is alive. It is more mechanical than most machines because it contains more feedback loops. Look at the horizon in the morning, and the command is different. The eyes move to distance, the visual field opens, the retina receives outdoor luminance. The melanopsin channel reports day, the SCN gets its timing edge, The endocrine system shifts out of night mode. The balance system receives a stable reference. The screen has not yet compressed the world to 30 centimeters. You felt the beginning of this at the start, when your eyes left the near field and moved toward a distant line. The effect was small because the act was small, but small inputs repeated at the correct phase can steer oscillators. A clock does not need a hammer. It needs a pulse at the right time. The horizon is not telling you anything new. It is telling your body what time it is. Tomorrow morning, step outside. Not for peace, not for clarity, not for mindfulness. Do it to operate the machine correctly. The horizon is still there. The calibration rail is still waiting.